Okay, good afternoon. Thank you for joining today's webinar. The title is New Technologies and Research in Residential Gas Water Heating. Today we'll discuss three interesting topics with three great speakers. We'll discuss methane emissions from tankless water heaters, advances with combined space and water heating systems, and residential gas-fired heat pump water heaters as well. My name is Paul Glanville from GTI, and I'll be your moderator today. A few items here, some ACEEE items I'd like to bring to your attention. If this is your first experience with this virtual conference, just know that your screen is customizable. You can move things around, play with the widgets. I'd recommend that you make it the best that you'd like as you're watching this webinar here. Also, you may see on your screen that the presentations can be downloaded as PDFs from the resource list there for you to take with you. All of you that can hear me speaking now, except for the speakers here, are in listen-only mode. So that means if you want to send a question to any of the speakers today, please use the question and answer box during the webcast. And what we'll do is that we'll collect the questions for each speaker, and at the end of each individual presentation, we'll try to address those. And if we have any extras, we'll handle those at the end in the Zoom chat. And also too, in terms of the presentations, the recordings will be available through the Engagement Hub in a few days, so just take a look at that. And then finally, when we're all wrapped up here, we will have a chat room afterwards, and you'll see the link to the Zoom chat on your screen as well. We'd also like to acknowledge the sponsors for this conference. You've seen their logos here, and they'll pop up on the next slide. We're going to go ahead and advance here. Let's see if I can get the click. Very good. All right, these are our platinum sponsors here, Ream and A.O. Smith. So let's all appreciate their support. And there are silver sponsors as well, which are shown here. So again, thank you for your support for this virtual conference. Okay, now I'm going to go ahead and introduce our first speaker here. And the topic here is methane emissions from tankless water heaters. Aaron Benetti joined GTI, a colleague of mine, in our energy and utilization group in 2017. Prior work in the refining industry for 6 years. She's had a lot of experience with different types of research and development projects, but in some cases has focused on methane emissions, both from equipment and from energy systems as well. And so excited to share some of the newer findings today. And that's both in the field and also in the laboratory. She earned her Bachelor's of Science from University of California, Davis in chemical engineering, and is a licensed professional engineer as well. So let's welcome Erin here, and let's go ahead and get started.
Thanks, Paul. And before I kick off the presentation, I do just want to acknowledge both Paul and the other engineers at GTI who helped assist with this project. There was a lot of work that went into it, and so I appreciate their work that allows me to present on this today. So as Paul mentioned, I'll be talking about methane emissions from tankless water heaters. And I first want to just put this in the context of methane emissions in general, and then specifically methane emissions beyond the meter. So why are we interested in methane? It's a potent greenhouse gas. When you're looking at gas equipment, methane is the primary component of natural gas. And although the methane emissions in general, when we're looking at greenhouse gas inventories on a country basis, a city basis, methane emissions on a mass basis are much smaller than CO2, for example, but they're a much more potent greenhouse gas with 28 times the global warming potential of CO2. So there's a lot of attention paid to them. Historically, especially in inventories, a lot of work has gone into the natural gas production and distribution systems in terms of quantifying those methane emissions because they are so significant. But with a number of recent studies and kind of a shift in focus to end-use emissions, both from piping as well as from equipment, we wanted to delve a little bit deeper into the question of how significant are methane emissions from residential end-use equipment. How well do the current emission factors that are available actually represent those emissions? And there have also been a number of recent field-based studies that have come out of Stanford as well as U of I that have indicated that the methane emissions, particularly from tankless water heaters, could be quite significant. So we wanted to address this question and particularly address it in a lab-based environment where we had some more control over the variables and repeatability, and we're also able to hone in on what the causes of methane emissions might be. So our goal was to quantify the methane emissions from a number of tankless water heaters, and from that to be able to develop representative emission factors in a number of operating modes and understanding how those operating modes might affect emissions. So why tankless? Why is that the equipment we started with when really the attention is all emissions beyond the meter? But we wanted to start with tankless for a number of reasons. One, because of their growing market presence, and also the factors that play into that growing market presence in that they are an environmentally conscious alternative that besides their operational benefits, some consumers will choose them because of their lower energy use and their lower greenhouse gas emissions. And so the question was, with their operating behavior, with their very cyclic operation that could lead to higher methane emissions, how does that affect the environmental choice as well? And beyond the operational behavior, the heavy cycling that you see with tankless water heaters with each draw, some other factors that we were considering as we thought about how methane emissions might be significant were the burner design. You see a number of varieties of burner types in tankless water heaters, from cartridge to mesh style, different number of ignition points. You also see a variety of modulation control strategies. So particularly as that hot water demand changes from low to high, you might see a single modulating gas valve or various stages that come on and off to meet the demand. And then finally, the general controls such as the airflow controls and others. So as we were considering these and in selecting the 3 water heaters we tested, we tried to select 3 that kind of covered the gamut of those design changes. So unit 1 that we looked at was a non-condensing up-fired unit, had a cartridge-style burner modules that would, they were both had some staging individually for those modules and also would come on and off to meet demand. For units 2 and 3 that we tested, they were both down-fired units with really tight control of the excess air, both with mesh-style burners. And the main difference between these was that one of them had a single point ignition and a single gas valve that would fully modulate over the entire range of operation. So there were no portions of the burner that were turning on and off to meet the demand. Whereas the next one did have 2 stages that would ignite or extinguish as the hot water draw changed. I'm going to spend a little bit of time talking about the setup of the experiment and the testing, and particularly because I want to emphasize the challenges that come with trying to capture the full firing methane emissions from tankless water heaters. Oftentimes we'll see emission factors that are reflective of the steady state emissions, and here we really wanted to capture the full methane emissions from the tankless water heater. And the challenge that comes with that is, first, the really large range in concentrations that you're going to be measuring in the exhaust of the water heater, everything from over 8,000 ppm when you're directly measuring the exhaust concentration of methane down to less than 1. And just for context, about 2 ppm is what we have just in ambient air when you're outside, a little less than 2 ppm. So we're looking at subatmospheric methane concentrations during steady state. And then also the peaks of methane emissions that you see are highly transient, with that 8,000 ppm point maybe lasting just 1 or 2 seconds and then quickly settling out. And we approached this in a number of ways, one with a dual analyzer system. So we had one analyzer that had high ppm range and a really fast response time to be able to catch those transient peaks of methane emissions. And then another with a very, very accurate ppb resolution to be able to measure the steady state very low concentrations of methane. Other variables that we were measuring, gas input with a high-resolution gas meter, water flow, and others, and measuring these in different operational modes. To calculate the methane emissions from the water heater, we took the directly measured exhaust gas concentrations of oxygen, CO2, methane, and combined that with the high-resolution gas input that was measured and used a mass balance approach to calculate the exhaust gas mass flow rate. And this method is really great during combustion and doesn't work so well during those transient periods that we were really interested in capturing and quantifying the methane emissions during ignition and extinction. And so to supplement that method, we also utilized direct exhaust flow measurements using a pitot tube in the exhaust to understand what those transient flow patterns were during pre and post purge and during the ramp up and the ignition. So the combination of that exhaust gas mass flow rate and the measured methane concentration gave us our emission rate throughout the operation of the water heater. I'm going to jump now into the three types of tests that we ran and some of the highlights of the results for each of them. So we ran three tests. First, just a steady state max flow test, then a modulation test, and then a 24-hour simulated use case. So for our baseline tests, it's the max hot water draw to meet 125 F outlet. And so we just turned on the water heater, let it run for about 20 minutes, turned it off again. And that was to understand the ignition emissions and also the emissions from the burner when it's operating at its design gas input. So first, what do we see from this? One, the majority of the emissions are coming from the ignition and extinction. And we'll see this on the plot on the left where we see the ignition and extinction emissions. We're looking at about 100 milligrams per event. And then on the right, the graph is showing the steady state emissions. For units 2 and 3, we're looking at almost zero emissions during steady state. No methane being emitted, and even some methane being consumed from the combustion air that's being provided to the burner. In contrast, unit 1, which was the cartridge style, non-tight control of excess air and upflow, non-condensing, did show steady state emissions that and if you compare that to the ignition extinction emissions, which is sometimes a good way of just putting it in context, about 3 minutes of operation of unit 1 at steady state would be equivalent to an ignition or an extinction emission. For the modulation tests, we're interested in understanding when you already have an ongoing draw and it changes whether from a faucet being turned on or off, someone finishes a shower and the dishwasher is still running, how does that affect emissions? And so the plot on the bottom, I just want to highlight the fact that where we saw an increase in emissions from modulation was always associated with one of the phases of the burner extinguishing or igniting. So on the far left, that's the water heater coming on, and far right is the water heater turning off at the end of the testing. And in between that, wherever we see a spike of methane emissions was always from one of those stages of the burner turning on and off. You'll notice for unit 2, which is the orange bars, we only have one point when there were any emissions from modulation, and that was caused by the burner actually turning off briefly. Everywhere else, it was just modulating between various firing rates, and we didn't see any increase in emissions. The final test that we ran was a 24-hour simulated use test, and this was mimicking the DOE efficiency testing high usage case, so 14 draws, 84 gallons a day. What I want to highlight here is the total methane emissions for a typical representative day. We're looking at roughly 2 to 3 grams of methane a day. And the majority of that, again, is from the ignition and extinction events. And that ends up equating to about 0.27 to 0.36% of the natural gas. But I want to emphasize that these results are very specific to the firing pattern that was tested. And so this is 14 draws a day. Sometimes from field testing that we've done, we've seen maybe 40 or more draws per day. And these total grams per day and percent of methane emitted will change based off the number of ignition and extinction events that occur. So many short draws are going to have a much bigger impact on methane emissions than a few really long draws throughout the day. So summary of results. Again, ignition extinction, for every one of the water heaters that we tested, we saw that puffing, and that was the majority of where we observed emissions. Again, during modulation, depending on the burner design or the modulation design, whether or not portions of the burner were igniting or extinguishing had the biggest impact on emissions. And then for steady state operation, when you do have one of those longer draws, the burner design and the firing rate both will have an effect on the overall emissions. So hopefully it's bigger on some of your screens, but this steady state emissions rate versus firing rate plot that you see on the right here shows that for tankless water heater number 2, at all firing rates, we're seeing no methane emissions. For the other 2 units that we tested, there were methane emissions at each one of the rates that were tested during the modulation test. However, when you look at it on a grams of methane emitted per gram of natural gas that's being supplied to the water heater, that tends to go down as you get closer to the design firing rate of the water heater. So putting this in context in the whole home, what do these methane emissions that are coming from the operation of the water heater mean? How big and how significant is this? So I put this into context. On the left, this is the emissions just from the water heater itself. A typical 96 UEF water heater in a typical home drawing 84 gallons a day. Those methane emissions are about 2.6 of the total full fuel cycle emissions from the water heater. So that's including in the gray both the CO2 emissions from the actual combustion in the home, as well as the blue pie piece, the upstream emissions from the natural gas system and the upstream electric system. When you put that in the context of the emissions from an entire home, then that drops to about 0.3% of the total emissions. So in the last 30 seconds or so that I have left, what are we looking to do next? First, we want to continue to understand emissions from other pieces of residential equipment. Are we going to see similar patterns in furnaces and other types of water heaters? And to do that, we also need to collaborate and develop consistent test methods. There see a lot of variety between field tests and lab tests and some of the kind of cutting edge research that's been coming out recently. And so we want to collaborate to get some consistent test methods for this. And then finally, using the learnings from these tests as we are able to look at more equipment to develop mitigation strategies for where we identify it's an issue. So with that, I will close. My email is here if anyone has any more detailed questions, or I think that we have some opportunity for Q&A now and after the session.
Great presentation. Thank you, Erin. I'm looking here. I see one question in the chat box, and I'm going to read that to you now, Erin. This comes from Kyle Gusenkamp. Great work. At the measured 0.32% emission, what would the UEF need to be for a unit that had 0 emissions in order for both units to have the same CO2 equivalent impact?
Okay, let me. I'm gonna reread that to myself again, Paul, as well, to make sure I'm following it. So when I guess one clarification, for a unit that had zero emissions, I guess the main thing is, So I think that we're going to be seeing with the 0.32% emissions, regardless of the UEF, we're going to continue to see the methane emissions there. So I would encourage the person who asked that question to reach out to me directly. I would need to think about this one a little more to see when you're going to have the same CO2 equivalent impact. I think as long as you are, I would need to work that out. So I think it's the comparison of the methane versus zero emissions CO2. Where does that balancing point come? I don't have an answer right off the top, but I can move on to the next question and think about that one and respond to this person directly.
Great, go ahead. Since you've got the Q&A window open there, Aaron, why don't you go ahead and pick one of the two, and we can save the unanswered one for later.
Yeah. Okay. One, it looks like David Wynarski from PNNL asked, with the more typical 40 to 50 firings a day, would you expect more like 8 to 9% of greenhouse gas emissions? And so, and when you're looking at that, just in the context of the water heater itself, you'd probably see an increase in the percent from 0.32 to probably more like 0.9 or so percent of the natural gas being emitted. So when you look at that kind of in the context of the total greenhouse gas emissions of the water heater, yeah, about 3 times higher than the 2.6%. So 8 to 9% sounds about right. Let's see. Do I have time for one more, Paul?
It looks like a zinger, so why don't you go for it?
Any conclusions about whether tankless are better or worse than tank heaters in terms of methane emissions? All right. So in terms of methane emissions themselves, it becomes a trade-off. And we haven't done the lab testing of the tank heaters, but I can speak a little bit to some other research that's come out from Stanford, where with the much fewer firing events for tank heaters, you're not seeing a lot of methane emissions from that ignition and extinction. The contrast is that many tank heaters will have pilot lights that tend to have low levels of methane emissions, very low levels of methane emissions continuously. And so the methane question it kind of depends on whether or not the tank heater has a pilot light. When you look at CO2 equivalent emissions in total, generally the efficiency, the higher efficiency of the tank heater still has it come out a little bit ahead, or sorry, the higher efficiency of the tankless heater has it come out a little bit ahead in terms of overall CO2 equivalent emissions than your standard tank heater.
Great, handled that zinger well. Awesome. Well, let's give a virtual round of applause for Aaron. We're going to move on to the next speaker here. So next speaker is Steve Bagshaw from iFlow. He's been with iFlow he's been in the construction industry for 30 years with a focus on plumbing and HVAC, with extensive experience with product development and R&D around domestic hot water heating solutions that leverage tankless water heaters that we were just talking about, and boilers as well as heat engines. He's presently the Vice President of Sales at iFlow, and let's welcome Steve here to the virtual podium.
Great, thank you, Paul. Appreciate that. I hope all can hear. So in this segment, we're going to be looking at improvements in combination systems. From the ACEEE seminars that you'll have listened to yesterday, today, and that you will listen to next week as well. Most of those will be focusing on the newest innovation and approaches to water heating. But in this presentation, we at iFlow want to expand the uses of hot water well beyond just the domestic hot water delivery capability. We can use the excellent efficiency of heat pump water heaters, of condensing tankless water heaters, of combi boilers, even boilers, to do forced air heating as well. In its simplest form, a combi system really uses the hot water through a hydronic coil, an air handler, for example, if you will, to provide the forced air heating and replaces really the need for a traditional furnace. So let's take a look. So an air handler, so we at iFlow, for example, we can work with any tankless water heater in the market. So whether it's Navien, Rinnai, Noritz, Takagi, Rheem, Smith, we can work with all of those brands. but we can also work with any of the combi boilers, any of the wall-hung boilers. We can work with any of the tank-type water heaters or even heat pump water heaters. And even with a non-gas, a non-water-based solution, we can even work with heat pumps. So the air handler delivers the air through the home, so it's the air distribution system through the home, and we pair with any of the heat sources that are available. When I mentioned the heat pumps, so we can combine with the, let's say, the water-based system and the heat pump, so you can take advantage of the COPs in the seasons, let's say in the shoulder seasons, but then go to a gas source for the winter if needed. So we can deal with all of those different options. Sorry. So in a lot of what you've been hearing with ACEEE would be about the tank to tankless switch out, or using the efficiency of the tankless system. So if you're going to change, this is a traditional system. No, this is a tankless system where we've taken out the tank type water heater. For example, we've gone with a tank water heater or a tankless water heater for the domestic water, and then you'll typically have a furnace in there as well. So you have 2 gas lines, one for each of the appliances, and then you'll have 2 exhaust lines as well, 2 vents to exhaust 2 intakes, if you will. Sorry, the order of that was it's a little mixed up, but nonetheless. So for the furnace, is there anything we can do with the furnace? So we changed tank for tankless. Now we still have the furnace in place. So is there something we can do better? Do we need to do something better? So let's take a look at some results, and these are from GTI's study. So GTI, I'll go back one slide, so that was a little bit of a mix-up. So actually GTI did a study that was commissioned by NIA, and it looked specifically at the iFlow with a Navien combination and compared that to some of the existing options in the field. One was a furnace, so this is a 95% AFUE furnace. And what they did is they measured it to the part loads, replicating shoulder seasons in a number of different geographic locations. So each of these bars represents a different geographic location. The bar in blue represents Madison, Wisconsin. So that's a fairly cold weather area. The orange bar represents Albany, New York. The gray represents Portland, Oregon. The yellow represents LA. And the green is Birmingham, Alabama, for kind of the southeast and the humidity of the southeast. So, but what you see though is the demand, the heating demand really is in this 3,000 BTUs to 30,000 BTU range. So even in the cold weather areas, we're really not seeing a lot of demand in the, let's say, the 30 to 60,000 BTU range. So this is tested with a 60,000 BTU furnace in a 1,600 square foot home. So they've replicated that. That's the scenario we're testing to. But as you see, by the red line, the 95% AFUE is often not reached because the unit is cycling. You know, to deliver 12,000 BTUs or 18,000 BTUs when you've got a 60,000 BTU furnace, you'll be cycling on and off a lot. And every time you cycle, unfortunately, you'll lose efficiency. So I guess the question is, can we do something better? So in the GTI NIA report, GTI tested traditional combi systems that you would see in green. You have the furnace performance to those scenarios in red, and then you have the performance of the iFlow with the Navien. So we see that in the area, and let's see. We see in the area in green, that's the difference between the red and the orange lines. That's your efficiency improvement, and we gain that by being able to modulate to much better rates. So the tankless water heater that was used in this was an Avian 180A. The minimum input is 15,000 BTUs, so much different than a single stage furnace with a performance of minimum input of 60,000 BTUs. So we're able to modulate much lower and less and cycle less. And as you heard from Aaron talking about the emissions, when you're not cycling the burner, when you're just modulating up and down, you're seeing much lower emission rates as well. So there's some definite advantages to less cycling, both on the gas saving side, but also on the environment side. So back to our furnace scenario. So we saw by the GTI NEA report that there looks to be some potential advantage of using a combi system over some furnaces in the market. So let's look at what we can do. So by removing the furnace, which has its own burner and its own intake and exhaust, and switching over to using the tankless as our heat engine, and then just off the domestic lines, we bring a T, and that T will bring hot water into the hydronic coil, and then with this pump, we'll push it back into the cold. So for the heating circuit, it basically follows hot out of the tankless into the air handler with the pump back into the cold inlet of the tankless and circulates. So really what we're doing is we're using the efficiency and modulation of the tankless as our heat engine for now the heating side as well. So we're able to use the advantages of the tankless and now apply to the heating side. So a side-by-side comparison, we're looking at basically a tank-type water heater and a furnace, which would typically be your builder spec baseline for North America, and we're switching over to a tankless water heater and an air handler. Only one gas line, only one vent, one less penetration through the exterior envelope because we've got one less vent, and installations that'll go quicker, and the footprint will be much smaller. So there are many advantages to looking at that in addition to the efficiency and emissions reductions. So what makes a superior performing combination system? So can we just take any air handler, pair it with any water heater, and create a good performing system? And the answer is unfortunately not. CSA has a standard called P911. It's a standard that was developed to determine the performance of combined systems. So when you do pair a boiler, a tankless, a combi boiler, and pair that with an air handler, what type of efficiencies do you get? So there is a standard out there. There's also ASHRAE 124 that is a standard that also gives you. So there are two standards out there that are available. NRCan has actually listed this on their website. So the NRCan website has all of the systems that have been tested to date. They are listed there for public consumption. So I'm not talking out of class here. This is all available. And if you go to the NRCan website, you can actually download all of the results or put in whatever criteria you're looking for. I don't know how clear this is on your screen. It's probably quite small, but the range is from 0.72 to 0.98. So you see that there is significant variability between let's say a good system and let's say the best system. So we're going to look at kind of what makes a better system. So this is a condensed snapshot of the results, and I'm just going to look at a few of them. So, and this I'm not when I'm looking at different combinations here. Again, this is all public information. I'm not trying to bash any of the competitors out there. What I'm trying to do is show you that there is some significant variability in the combi systems out there. So for example, in this we have the Rinnai RU160IN. So this is the down-fired new Rinnai Sensei model, and it is paired with a high-velocity air handler. This is an ESP air handler out of Edmonton with a UPS 1558 Grundfos, and it scored a score of 0.72. That same Rinnai air handler, the RU160IN, the exact same air handler, was paired with the Aspen air handler, their AFLM model, with the TACO 008 pump, and they scored 0.73. We now look at the same Rinnai engine, the RU160IN, with the iFlow, our 18-inch unit, and we scored a 0.94. So again, I'm not doing this to point out, how I'm pointing this out, or I'm identifying this to point out really the differences in equipment. So again, not just by pairing the air handler with the same heat source, the same pump, you would expect that the results should be similar if all air handlers were built the same, but they're not, unfortunately. And you can see that there's some significant variability from 22 points of difference. Let's look at another example. So here you have the Navion NP180A paired with the high velocity systems, and they scored a 0.86. With that same engine, the NP180A, the iFlow scored a 0.98. So again, a 12% difference in terms of efficiency. So all to say that the systems are not made the same. In addition, we have the Rheem condensing tankless, so they're condensing residential tankless, 95%. AFUE direct vent with their air handler, and they scored between 80 and 82. So again, these are, all the different manufacturers will have different air handlers that they've tried, different combinations that they're testing with. But I guess the key here is with the same heat sources, you're seeing very different performances. And that's a result of the air handlers that they're using, not so much the heat sources, because the heat sources will all perform the same. So it's more of a comment of the air handlers and to show the variability. When you put those together in a matrix, you're going to get some very significant differences. So if I pair a Tier 1 water heater with a Tier 1 air handler, you're going to get results in the 92 to 98% range. If I pair a Tier 3 water heater with a Tier 3 air handler, I'm going to get 66 to 72% results. So there's some significant variability. So let's look at what makes those differences, what accounts for those differences. Again, this is small, so if any of you want a copy of this, please email me after, and I can supply you with this. But on the water heater side, if we put a heat pump water heater with a UEF of 3.0 for example, that's going to give you a good result. If we have a tankless water heater with a UEF of 0.95 or greater, with a turn down ratio of 10 to 1 or greater, that's going to get a good result. If it has an outdoor temperature sensor, similar to what a boiler would have in terms of being able to modulate the heat supply into the air handler, then it's going to get even better results. A combi boiler, again with a high turn down ratio, let's say 10 to 1 or better, again with that ability to adjust the supply into the air handler with an outdoor sensor, you're going to get good results. Boilers with greater than 60,000 BTUs with an AFUE of 95 or greater, with a good turn down ratio of 10 to 1 are going to get good results. So that's kind of how we identify on the heat source side, which type of burners, as Aaron mentioned, which type of burners, which type of AFUEs, which type of units will modulate to be able to give you that performance. Tier 2 examples, let's say a heat pump with UEF of 2 or greater, with a tankless unit that has, let's say, a UEF of 93, let's say a turn down not as high as 10 to 1, but maybe 8 to 1, that will give you a Tier 2 solution. A Tier 1 solution would be electric water heater, perhaps, tankless water heater that has a 5 to 1 turn down without any temperature adjustment control. A tank type water heater, where this is an Energy Star unit on the gas side. So that's how we kind of differentiate the heat sources. And then on the air handler side, we've got a number of different factors. So one is Ecm Blower. There are really two different categories of ECM. There's a constant CFM ECM, which is really the fully modulating type, and that's like a Gentech Eon blower or any of the similar many competitors' models. If you have a 4-row coil, right? If you have a 4-row coil or a 5-row coil, you're going to get some decent performance. So that will give you some good results. If we go down to stage 2, then we have the heat pump, or not the heat pump. Sorry, it's even hard to see on my screen here. A constant torque Ecm, which is basically got 5 settable tabs on it, so it's not fully modulating, but it's got a 5-step. Let's say a 3 or 4 row coil with the ability to adjust the pump speed a little bit. And then the tier 3 solution would be just a simple PSC motor, a 2-row coil with a single speed circulator. So these are the metrics that will really define the good, better, and best performers. And when you put them together, you see the variance in results that you get. So really, the conclusion here is, let's just go to the finish. That use your modulating condensing tankless, for example, as a provider, not just to domestic hot water, but also as an engine that most efficiently transfers heat to natural gas, and then you can apply that heat to the domestic side, of course, but also to the heating side. So we've kind of looked at some of the what combination systems are, how they perform differently, and we'll leave it at that. So I thank you for your time. If you have any questions, you can fire away now. Here are my contact details should you wish to reach us after. And as Paul mentioned, we will have a question and answer period after. So I think we have one question.
Steve, if you don't mind, great presentation. Really appreciate that. Yeah, exactly. Let's save it for after Mary's presentation, just to make sure we have adequate time. But let's give Steve a virtual round of applause. Excellent presentation. I see one question in there from Kevin. We'll get back to that when we're at the end of this overall session. So appreciate the flexibility there. Okay, our final speaker is Mary Sweeney. She came to GTI in 2010, also within the same energy utilization group as Aaron and myself. She focuses both on R&D benefit and cost analyses, market characterizations, and other investigations, and generally an all-around Swiss Army knife when it comes to working through these sticky R&D projects. So she earned her BA in Environmental Studies at the University of California, Santa Cruz, go Banana Slugs, and an MS in Natural Resources from University of Michigan. So let's go ahead and welcome Mary, give her a welcome to the virtual podium here.
Great. Thanks, Paul. I appreciate it. So I'm going to be talking today about the results from a currently wrapping up demonstration project we have in California on residential gas heat pump water heaters. Like Aaron, I'd like to take a quick moment here at the top to recognize that this was a huge team effort, both within GTI and with project partners up and down the state. So we really had a lot of support and a lot of technical expertise was brought to bear on this topic. Before I dive into the specifics of the project itself, I wanted to talk a little bit about the motivation, what brought us here. Gas water heaters operate in 3/4 of California homes, so you're looking at an installed base of roughly 9 million units. Looking specifically within Southern California Gas's territory, roughly 95% of homes use natural gas for water heating, the vast majority of which are minimum or low efficiency. So, lots of opportunity here. That being said, anyone familiar with the water heating arena knows that the value proposition is difficult. Ultimately, the annual expenditures of a home on their water heating are relatively modest. So any energy savings that you gain usually are difficult or challenging, at least, to offset, usually with higher equipment costs, sometimes with higher installation costs with infrastructure upgrades. Likewise with water heating, reliability is really key. There's an expectation amongst consumers that they don't need to touch their water heater for years and years and years, low, no maintenance. It's also an area where you see a certain degree of do-it-yourself installs. So requiring kind of more of a plug-and-play friendly option for individuals is pretty important as well. With that in mind, I wanted to talk a little bit about the specifics of the water heater that we used for this demonstration. So this is a direct-fired ammonia water single effect absorption cycle heat pump. It's integrated into a storage tank with heat recovery as well. Because the units were going into Southern California, they of course were certified to South Coast Air Quality Management standards for ultra-low NOx. So you can sort of see some specs here as well for the balance of the system. It's also important to note that this effort is a follow-on from several efforts that have been over the past 10 years to develop this technology. So this is currently deemed the 4th generation unit. Other units have been installed in various locations across the US, and you can kind of see from this graph, we've seen sort of steady increases in efficiency as well as some improvements in reliability from these past efforts. So this 4th gen effort was really intended to build upon the lessons learned and efforts from the past field work. So this project had a variety of objectives. Of course, we wanted to demonstrate substantial therm savings. We were targeting 50% or more over baseline water heating systems at 5 single-family homes in the Los Angeles basin. We also partnered with Southern California Gas to perform some additional laboratory testing at their Engineering Analysis Center. We're focusing again on some kind of enhanced reliability testing as well as some additional emissions testing. We worked with our other project team members outside of GTI on developing a simulation model that would allow basically simple comparisons between the gas heat pump water heater and other water heating options. Would also serve as sort of a design sizing guide. We performed a Title 24 analysis, looking again, to provide guidance on how to reduce codes and standards barriers and introduce this as a potential option amongst the prescriptive options of Title 24. We also performed market research, looking forward towards commercialization for the technology, how it would be received by the market, kind of identifying some key messaging and tipping points to keep in mind moving forward. And of course, we also had outreach and education activities throughout this project. So it was a lot of varied activities, and so I'm going to try to cram a lot in here today, so I apologize if I'm moving quickly. For the sake of the demonstration sites, we put them into 2 clusters across the LA basin, kind of a northwest cluster and a southerly cluster. The cluster is slightly more coastal, had a more mild climate, so we had a little bit of variation there. Likewise, there was a unit installed at the Engineering Analysis Center at SoCalGas for their laboratory testing. The 5 residential host sites, they were all single-family homes. We did have small variations between them. All of the water heaters were installed in the garage, which is very common in California. Most of them were minimal or low efficiency, with the exception of Site 5, which did have a power vent unit, so a slightly higher EF. Likewise, most of the homes had 4 occupants, again, with the exception of Site 5, which sort of had 2 permanent occupants and a 3rd intermittent occupant. So we saw some minor variations in some of these behavioral patterns. I've got some photos here so you can kind of see the gas heat pump water heaters were installed in parallel with the existing water heater. I want to clarify that they were never operated at the same time. The intention was to retain the baseline system in the event that the gas heat pump water heater needed to be repaired or have any kind of maintenance performed, that we could simply valve over for the convenience of the homeowner. But when that gas heat pump operated, it operated on its own. So of course, we're always thinking of looking at therm saved when we think of field evaluations. We're looking for the big energy efficiency numbers and the savings numbers, but there were several other goals to the field evaluation as well for this. Beyond just site-specific savings, we wanted to be able to assess reliability issues. identify any kind of pathways for predictive maintenance moving forward. Likewise, we wanted to take those site-specific savings and normalize them across local and behavioral conditions to draw out a more general case. We also wanted to really understand the experience. What are the installation barriers? What was the retrofit? What are the kind of challenges that would need to be faced by installers that were taking on this new system? And then, of course, as always, quantifying host comfort. We did perform qualitative surveys with the host before and after installation, but we also wanted to look into the data to see, are there instances of running out of hot water? Are there opportunities for innovative controls or some type of minimal use of supplemental heating is necessary? So we wanted to look at some of those. Wanted to look at the data set to address some of these other questions. This is also worthwhile to note, as I mentioned, previous field demonstrations had been in other locations. So we had this opportunity here in California to look at some of the California-specific nuances as well. You'll notice in one of these photos, the gas heat pump water heater doesn't require the standard 18-inch stand for flammable vapors that we typically see in California. Likewise, we instituted seismic straps for the first time with this unit and some of the other California-specific requirements. So we saw substantial gas savings across all 5 sites. The graph to the right, you'll see sort of 3 sets of lines. Obviously, the large dashed line is the baseline water heating system, some natural variation there depending on behavioral patterns and the particular specs of the system. For the gas heat pump water heater, you'll see 2 lines, a solid line, which shows the results across the full monitoring period, and then kind of a dotted line, months. As you see, the first 6 months showed particularly strong performance. This is partly because they went in the summer. They went in the summer of 2018 specifically, where LA saw some record-breaking heat. A lot of these units were in the garage, and those garages were pretty piping hot. But ultimately, you can see from the table, we saw savings, therm savings anywhere between 37 and 54%, varying a little bit dependent upon baseline. So very strong numbers there. Likewise, we looked at sort of the cycle COPs. You can sort of see that for sites 2 and 5 were in the milder climate. They show slightly higher performance. We did have sort of a decreasing firing rate issue over time at site 2. So you kind of see their relationship here is a little bit inverse to the other sites. But ultimately, these numbers were heavily dependent on the internal TCs. But nonetheless, all of this field data was kind of taken into account as we developed through a model simulation process. So we developed a user-friendly spreadsheet-based modeling tool. We developed 2 versions, kind of a very basic version that kind of anybody could sort of drive, and use as a design sizing tool and kind of compare and contrast water heating options. We then have a slightly more detailed version for engineers and technical experts that might want to go in and alter some of the variables or some of the assumptions of the model, tinker a little bit more in the back room. As I mentioned, there was a Title 24 analysis completed as well that looked at statewide energy impacts, cost effectiveness, greenhouse gas and water impacts. And there was a framework developed for how best to potentially integrate the gas heat pump water heater into the residential alternative calculation method, kind of some first steps of what that process might look like. In addition, we did do some third-party market research as well to kind of look at the market response to the commercialization of this new technology class. So the market research was approached sort of with 2 stages, a qualitative and then a quantitative stage. The qualitative stage was a series of in-depth interviews followed by a series of focus groups. This is focused primarily, of course, with contractors, plumbers, home energy improvement professionals to kind of gauge their experience and initial reception for the technology. The input and feedback that we got through those discussions then informed the design of a quantitative survey, 2 surveys actually, that were distributed nationwide, one targeting homeowners, another targeting contractors. The lessons learned from the results that we got through those surveys, we were able to build kind of a what's commonly termed a SWOT analysis, a strength, weaknesses, opportunities, and threats, which is briefly summarized by these 4 boxes you see here. but I'll take a couple last few minutes to dive into some of our key findings. So based on the results that we had in our discussions and surveys with contractors, we found that the majority felt that they could sell this product. So they had very positive reception to it. And of course, cited that the initial cost would be the primary obstacle for consumer acceptance. Not a significant surprise. That was anticipated, but always good to have that confirmed. It was also determined that approximately 1/3 of single-family homes that currently have natural gas or propane service were likely to be prime customers for gas heat pump water heaters. I won't dive into the specifics here, but you can see there's a handful of bullets that kind of identify customers that might be considered a beachhead market, an early market, as potential adopters for the technology. We also used a series of conjoint questions to kind of zero in on sort of the economic sweet spot. And we found that with this target audience, they were significantly more likely to purchase the gas heat pump water heater over the standard tank options, provided that the purchase price difference was $1,000 or less. So we basically varied the pricing models for each survey and used a series of questions to kind of zero in on where that tipping point lay. I will wrap this up with two last graphs that highlight a specific portion of the market research. So we wanted to also look at share of preference on a regional basis. So this is, you can kind of see in this table here, we presented a price point range. Depending on each respondent was given a specific price point, and their specific price points fell within this range overall. We gave them a price point for a standard tank, a tankless, and a gas heat pump water heater. We varied the pricing, as I mentioned, across regions, and we came out with this sort of share of preference. So I thought this was particularly interesting because it sort of shows the regionality, the concerns that folks might have around their particular low conditions around energy efficiency, as well as natural gas and electricity pricing. So you can kind of see the rise of horizontal axis as the unit price gets more expensive. Of course, the share of preference goes down for the gas heat pump water heater. But I thought it was interesting to see, you know, comparing and contrasting, for example, the response from Southern California homeowners versus those in the Pacific Northwest. Some interesting responses here. I think also I'll make a note that we did group our respondents into whether they had a small capacity water heater or a larger, medium or larger capacity water heater. So these respondents all had a water heater that was 40 gallons or less. We then, if we look at the larger water heaters, you see that a lot of this variation starts to disappear. So these were folks that had anything above a 40-gallon water heater. You can see it's a much tighter, we lose the regional variation until we get to sort of a certain price point, and then it sort of slowly starts to emerge again. But in general, the share of preference is, of course, much higher with the medium and large water heater users, not particularly surprising because we would expect this to be more cost effective for those circumstances. So next steps, a final report summarizing all of these activities and all of these findings is currently with CEC for their final review. We are optimistic that they'll be able to publish it hopefully by the end of 2020, but depending on delays, potentially early next year. We are also currently looking at some additional currently beginning to launch an additional demonstration project that would look across North America, sites in the US and Canada to place units as well. So that's early stages getting off the ground right now, but we're looking forward to having even more varied results in the future. And with that, here's my contact information if there's extra questions. Thank you.
Excellent presentation. Let's give a final virtual round of applause for Mary and the rest of the speakers. We've got a few minutes left here. We did kind of cut short Steve's Q&A session. So if Steve can come back in, we're going to go to Kevin's question here about how demand is prioritized and if the water heater has to be oversized to handle the full winter heating and domestic hot water load.
And the answer is no. Typically, it doesn't. With your tankless water heater, for example, you'll be using that for, let's say, a family of four showers a day, a load of laundry a day, dishwasher a day. If you're using it for 2 hours maximum, it's probably more than the average family would use. That means there's 22 hours of the day that it's left on the wall doing nothing. We can easily double duty it and apply it on the heating side without any major interruption of the system at all, and really no need to prioritize. In addition, the the burners of the tankless units are usually significantly high. You're talking 150 to 200,000 BTUs. The heating loads will be varied, but usually much lower than that. So you can often run one shower and the heating load simultaneously without any problem, so you don't actually need domestic priority.
Thanks, Steve. Mary, can you do a lightning question? Does the actual cost of the gas heat pump water heater fall within the range on slide 14?
Sure. So the gas heat pump water heater right now is a pre-commercial prototype. So it doesn't really have a formal commercialized cost. I will say that the targeted cost is expected to fall on the lower end of that range that was offered. But yeah, there's not an official price tag yet.
Excellent. Thank you, everyone, for your attention here. I do want to direct everyone to the Zoom chat that we're all going to be heading to right now. And also, please join us for the Shameless Commerce later today, just to see all the neat things that are going to be discussed there. Thank you, everyone. Have a great rest of your day.